Okay guys, this is the video for example 6.9, which is found at the top of page 9 of your notes outline. This would be the example that I didn't quite finish on Monday during class. I'm going to do the entire example repeated from beginning to end. Again, it starts out by saying using the following equations and the Hess's law process to determine the enthalpy of formation of 1 mole of NO gas from its reactants. So we're going to start out with writing that final equation that we're trying to get. We know that we want 1 mole of NO gas. That means we want the coefficient in front of the NO to be a 1, and it's forming from its elements. So N2 gas plus, I got it kind of tight there, let me rewrite that. N2 gas plus O2 gas. And in order to balance this equation, we have 2 of each of N and O on the left and only 1 of each on the right. So we need a coefficient of 1/2 on the left-hand side for each, remembering that fractional coefficients are acceptable in thermochemistry. And eventually what we're trying to do is determine the delta H for this particular equation. So I'm going to go ahead and write delta H equals off to the right, so I know that's my ultimate goal. And then just reviewing, we got through the first 2 equations on this. I'm going to call these equations 1, 2, and 3 up above, so when I'm referring to them, you know which one I'm speaking of. What I recommend you do is actually work left to right. So we come down here and see that the first thing we want to do is end up with N2 gas on the left-hand side of the equation with a coefficient of 1/2. So if we go back up to the equations that we have to work with, equation 1 is where you'll find the N2 gas. And you want to make sure you look through the others, equations 2 and 3, to ensure that N2 gas isn't found in either one of those, and it is not. So now we can see we have it on the proper side, the left-hand side, but we want a coefficient of 1/2, and we currently have a coefficient of 1. So what we're going to do is rewrite this equation, multiplying each current coefficient by 1/2 as we go, in order to get the coefficient in front of the N2 to be the proper coefficient. 1/2 times 3 is 3/2. Keeping my yields lined up. And then 1/2 times 2 will be a coefficient of 1, NH3 gas. And since we multiplied the entire equation by 1/2, we must also multiply the delta H by 1/2, which is the same thing as dividing by 2. You can write it either way. And again, I use parentheses just to emphasize my negative sign so I don't lose them along the way. And that'll take care of my N2. We'll worry about the other stuff later. We just keep working our way across left to right. So now we go on to O2 gas. And we come up here, we've already used equation 1, so we're focusing on equations 2 and 3 now. And here's the dilemma we run into. O2 is found in both equations 2 and 3. So we have to determine how to handle that. And my suggestion to you is the best way to handle that is simply skip the O2 for now and move on to the NO gas. And the O2 will hopefully work itself out, and you'll see as we go through the process what I mean by that. So we come up here, and we've again already used equation 1. So in equations 2 and 3, where do we find the NO gas? And we find it right there on the right-hand side of equation 2. So it's on the side that we want. It's on the right-hand side. Unfortunately, it has the wrong coefficient. It has a coefficient of 4, and we want a coefficient of 1. So as we rewrite this equation, we're going to divide all coefficients by 4 as we go, and then also divide the associated delta H by 4. So starting here, working through one at a time. 4 divided by 4 will be 1, so it'll just be NH3 gas, plus 5 divided by 4 will be 5/4, just keep it as an improper fraction. O2 gas yields, and now 4 divided by 4 will give us my 1 NO gas. And then 6 divided by 4 will be 6/4. Let's at least reduce that. So that's 3/2 H2O gas. And then again, my associated delta H must also be divided by 4. Negative 906.2 divided by 4, off to the right. Now we've taken care of equations 1 and 2. Sometimes when you have 3 or more equations, it's a good idea to go ahead and do some preliminary canceling. So at this point, I'm going to look and see, is there anything that is found both on the left and the right-hand side of these equations and thus will be eliminated. And here's the first thing that will be. The NH3 gas is going to go. We have 1 mole of NH3 gas on both left and right. And then looking further, it looks like we have O2, H2O. Doesn't look like anything else will cancel. But hopefully at this point we're far enough along that we're going to be able to figure out how to manipulate equation 3 in order to finally get what we want. On this side we have the NO gas that we want, but we also have 3 halves H2O we need to get rid of. And H2O hasn't appeared anywhere over here. So perhaps we can use the H2O to guide us and determine how to manipulate that equation. That's one option. We can also look at this and say, okay, in the end, we also don't want any H2 down here, so we need to do something to get rid of this. So we could also use the H2 to guide us. We need to end up with 3 halves H2O on this side and 3 halves H2O on this side. So if we look at this equation, if we reverse this equation, we'll get the H2 over to this side to cancel this guy, and we'll get the H2O over to this side to cancel this guy. So it looks like we're going to reverse this equation, but at the same time as we're reversing it, we also need the coefficients in front of those 2 items to be 3 halves, and they're currently 1. So we're going to reverse and multiply by 3 halves, the most complicated of what we've done. So this comes over to the left and will appear as 3 halves H2O gas, and just take your time so you don't make any simple mistakes. Now these two go over to the right. So 3 halves times 1 will give us my 3 halves H2 gas, and 3 halves times 1 half. So we'll end up with, when we multiply fractions, 3 on the top and 4 on the bottom. So we'll end up with 3/4 O2 gas. And again, we reversed it, so now it's positive 241.8, and we also multiplied by 3 halves, which is the same thing as dividing by 2/3, since I already wrote my fraction line, but I'm going to be honest with you, it's going to be a lot easier for us if we write it that way. So positive 241.8 times 3 halves. Okay, again, we reversed it and we multiplied by 3 halves. So now we're ready to go ahead and start doing our canceling. So there's my 3 halves O2, H2O gas, my 3 halves H2O gas. Here's my 3 halves H2 gas, my 3 halves H2 gas, my 5/4 O2 gas, and my 3/4 O2 gas. So the 3/4 O2 gas will completely disappear, and the 5/4, 5 minus 3, will leave us with 2/4 remaining. And 2/4, when you carry it down, is the same thing as 1/2. So let's see if we have everything we're supposed to. There's my half N2 gas, half N2 gas. My half O2 gas, when I reduce that fraction, half O2 gas. And last but not least, my NO gas here. And then we need to take all of these to calculate our final delta H. How are we going to handle this one? Well, very simply, 241.8 times 3 divided by 2 plus negative 906.2 divided by 4. You're going to want to use parentheses there, plus negative 91.8 divided by 2. And when you're all said and done, that one comes out to 90.25 kilojoules. Now what I'd like you to do is actually take a moment to do this calculation, and let me say how that would proceed again in your calculator. And then I want you to carry through it so you're sure that you're getting this calculation correct. 241.8 times 3 divided by 2 plus parentheses, negative 906.2 divided by 4, close parentheses, plus parentheses, negative 91.8 divided by 2, close parentheses, and equals. And this will be your final answer. What you want to stay away from is calculating this, writing it off to the side, calculating off to the side, calculating off to the side, and re-entering them. It just introduces the opportunity for error when it comes to your calculator work. Now I'm going to go ahead and stop this video, and I'll start it again with a new video for section 6.7. So if you want to go back, you'll be able to see that this Hess's Law problem example 6.9 is an independent video.